Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we'll be looking at systems of linear equations, and we're going to start by looking at Cramer's rule. Now, just as a reminder, a system of linear equations is going to be a bunch of equations that solve for different variables all to the first power, added up, so in linear combination. We can write these in terms of matrices as one matrix that's the coefficients organized so that all the coefficients of variable x1 are in the first column, for x2 in the second column, all the way through n variables. And this times our column matrix of n variables. When you multiply these together, it can be set equal to a column matrix of these right-hand sides, the coefficients or the constants that each equation is equal to. And this is the matrix form for this. And this is convenient for solving these linear systems of equations because there are multiple techniques that are based on matrices. So the first of these is Cramer's rule, and Cramer's rule, it looks very complicated, but what it says is that if I evaluate the determinant of that matrix of coefficients, so the determinant of A, that is going to be related to all of the answers. So I'm going to take the determinant of A as the denominator for each of my x sub j, but for x sub j, I'm going to replace the jth column of A with B. So this is the notation here, the determinant of A augmented with B for substance J, or substance J, component J. And we can use it either using determinant notation or this other. Over here is the algorithm for this, and I'm not going to spend a lot of time on this because this is how you could program taking the determinant. And if you'll recall, this requires us to go through and do cofactors. But so what you're going to do is you're going to identify all the elements of A and B and how many equations you have, and then evaluate the determinant of A. Now, this is something that is key, is if the determinant of A is equal to 0, you're just going to need to follow this down and stop because there will not be a solution by Cramer's rule. Once you have the determinant of A, then we're going to go through and find the determinant of A that's augmented with B in the jth row. And so this is taking us through that decision making. So we're going to start with j equal 1 and go from j equal 1 to n, and then same thing with I. And so these are representing loops. And then we'll always make decisions. Once I'm out of the loop, then I can just leave. But if I'm leave those over here, and I'm going to go through and replace the jth column and then evaluate that determinant. And so this is going to get me the determinant for the numerator, and then I'll divide that by the determinant of A. And each one of those ratios, therefore, will get me the value of x. Now, I'm not going to have you write this as code to evaluate the determinant because Excel can do this. It is mdeterm. So the m at the beginning indicates that it's a matrix operation. So mdeterm. And then we're going to highlight the array enclosed in parenthesis. Now, the cool thing is, of course, is that I can do this from VBA also. So therefore, I really don't need to know how to program the determinant, because within Excel, I can just evaluate a determinant. So let's look at this in practice. So here is an example problem. We have the coefficient matrix A is going to be, the first column is 3, 11, 56, 17. The second column, -5, 16, 22, 66. The third is 47, 17, 11, -12. And the final column in A is 20, 10, -18, and 7. And then B is going to be the column vector or column matrix 18, 26, 34, and 82. So I have those already set up in Excel just to make it a little faster. So here is my A and here is my B. And what I want to do is I want to do the little augmented matrix for each one of these. So if I just copy this down here, then what I'm going to do is for X1, I want to take the B's and replace column 1. The way that I evaluate what X is equal to is using mdeterm. So I'm going to take the determinant of this matrix where the B's replaced the first column, and I'm going to divide it by the determinant of just A. And so X is equal to negative 1.1, and you can, add more digits if you wish. I can do this for all of the various variables. So let me just copy A, and I'm using Control-C, Control-V because I tend to use the keyboard more than the mouse. And then I'm going to use B, and I'll replace the second column for X2, the third column for X3, and the fourth column for X4. This formula, I want to always use the correct modified A matrix for the numerator, but the denominator will remain the same every time. So therefore, I'm going to insert $signs to indicate that I want to use absolute references there. And again, I'm doing that using the F4 key. And I can therefore come in and evaluate this for each of mine very simply. Now this works, but doing a determinant by hand is really hard unless the order or the size, the number of equations is small. And so we don't often do this, okay? I will also like to point out that you can, if we wanted to set up a macro, okay? So if I wanted to record a macro, let me do that down here. So I'm going to record a macro just so that we can see what it is. Control X. Then I could say that this is equal to mdeterm. Oh, wait, I want this one. Divided by mdeterm of this one. And I didn't open my parentheses, did I? Okay. Yep. I failed to open the parentheses. There, we've got it. And I can put in the $signs. Okay, so I got the same answer, and now then I'll stop recording. Let's look at our Visual Basic. And we can see here that it has written the code for how we want to do this, okay? And so you can use this technique also as a way to build an appropriate Visual Basic program to do the same thing. So in our next lesson, we're going to look at another matrix technique. So thank you for your time.